I mean, as you know, this is now the third time that we meet here, and the first time was about 2.5, 3 years ago, or something like that. And you could be forgiven for asking the question, well, have you not found it out? Have you not sort of found the solution? So what is different in developmental prosopagnosia? Where's progress? And what I would like to do today is just briefly tell you what we think we know, which is surprisingly little, and maybe also why progress is so slow. So, I mean, John showed a similar picture. So we know a lot about brain areas that are involved in face recognition. We don't really need to know the details. And in a way, when you are confronted with a phenomenon like people finding it extremely difficult to recognize faces, maybe the answer is really obvious. There must be something wrong with the bits in the brain that do faces. That should be the straightforward answer. And, well, it is actually not the case. So coming up with this is, coming up with an idea like this is quite natural, because it's sort of the medical model of how the mind and the brain work. The medical model assumes that sort of face recognition deficits can be understood sort of in a way that is not dissimilar to, say, kidney stones. If you have kidney stones, you can see them. There's a problem, there's something in the kidneys that you can actually image, and then there's also an obvious solution. You apply, I don't know, ultrasound or surgery, and then the pain is gone. That's straightforward, sort of obvious problem, obvious solution. And in a way, it would be lovely if face recognition deficits were like that I can point you to this area here and say, this is where your problem is. There's a gadget here that doesn't work properly for you, and we can see it. We can see it anatomically, we can see it functionally. Problem is we don't know quite how to fix it yet, but since we have sort of at least localized the faulty bit in your brain, we can just do it eventually, sort of whatever. The problem is that's simply not how the brain works, at least not in the case of developmental prosopagnosia. I mean, in some cases of acquired prosopagnosia, where a stroke actually has destroyed parts of the brain, that can be a fruitful approach, at least to understanding why certain things are no longer working. So we have many stroke patients have obvious deficits like hemiplegia, that they cannot move the opposite side, the side opposite of their body where the stroke occurred, or speech impediments. That is all pretty straightforward. In face processing, and especially in developmental prosopagnosia, it doesn't really work like that. And I think the reason is that there isn't really an obvious problem with the hardware of the brain. So John talked a little bit about these famous cables that run through the brain and connect different areas. And there's some evidence that maybe these cables aren't quite as well developed in people with face processing or face recognition deficits. But that's probably not so much a sort of hardwired anatomical problem, but more a problem of sort of maybe atypical learning processes. So even there, we cannot sort of have the faulty bit logic and saying, look, that's where it is, that's where something isn't right. So what we have been doing in the last 3 or 4 years is using electrical brain activity to see whether we can at least get some grip of the things that are typically not quite working in a typical way in prosopagnosia. And the nice thing about this electrical brain activity, some of you have, or lots of you have participated in our experiments, others have seen the labs where we record EEG from the scalp electrode, that is that we can actually trace the processing. So there's a face or whatever coming on the screen, and then we can actually have these different stages. So if you think about what face recognition actually involves, then there's a sort of clear, almost logical sequence of processing stages that you have to go through in order to ultimately recognize a face. So first of all, you have to perceive a face. Then you have to somehow compare whatever you have perceived to some, say, let's call it mental image, some represented visual memory of a particular individual that matches or does not match the face that you have in front of you. And that is sort of visual face recognition, you can say. The outcome of this process would be something like, that looks familiar. But that's, of course, not enough for face recognition. So you have to have another step where this, that looks familiar, is then translated into the appropriate retrieval of information about the identity. Now, someone with this face can only be my friend Peter. And then all kinds of information about Peter come up. So these stages all have to work perfectly well in order to actually recognize this thing in front of me as my friend Peter. And the question that we have asked is, which of these many stages may be different in prosopagnosia, and especially in developmental prosopagnosia. So there's lots of complicated models. So if I just cut a long story short, we found surprisingly often absolutely no difference, which maybe as a sort of anecdote for sort of life as a scientist, what you need to find in order to get into really good journals and sort of become rich and famous is find differences between groups. So what we're really always looking for is sort of big differences between you and our age-matched control groups. And it's much harder to actually find identity. And well, we still try to. We have now several papers that we try to publish where we say, look, prosopagnosics and people without phase processing difficulties are exactly the same, because we think that's just as important as demonstrating differences. But so in many cases, we found that there was absolutely no difference. I think John mentioned one of them, this N170 component here. So if we talk about these stages of phase processing, this N170 component that is sort of elicited about 1/5 of a second after a phase is presented on the screen, that's basically just saying, the brain saying, this is a phase rather than a non-phase stimulus. And this sort of differential response to phases as compared to non-phase controlled stimuli like houses is basically exactly the same in prosopagnosics, in developmental prosopagnosics, not in acquired prosopagnosics. So Bob, for example, did this test as well. And here, if I would show you Bob's data, there was basically no difference between phases and houses. But that's extremely unusual. So in the developmental prosopagnostics that we tested, there was basically no difference. So in a way, that shouldn't come as a terrible surprise, because all of you are able to perceptually discriminate between phases and houses. I mean, there is no problem in making this discrimination. But this early stage in phase processing, phase perception, is definitely not affected. What is atypical is an early perceptual response, the same N170 component when you do strange things to a phase. So John has already mentioned that when we're sort of presenting phases upright or upside down, in age-matched controls, there's this sort of N170 difference, larger and delayed N170 for inverted phases. So there's something about this sensory perceptual response to phases that differentiates between upright and inverted phases in control groups. And in our DP group, we didn't find that difference. Well, if anything, it goes in the other direction. So there's definitely something about treating these two types of phases very differently in people without prosopagnosia, and people with prosopagnosia somehow don't make that difference. In a recent study that we are currently preparing, we just sort of tried this in a slightly different way. Rather than turning phases upside down, we just scrambled the internal features here. So these two types of phases are obviously very different, and we were expecting that this early sensory response should also sort of register the difference between these scrambled phases and these sort of intact phases. And that's indeed the case for age-matched controls. You can see a big, slightly delayed, bigger response to this unexpected phase configuration. And in our DP group, there's absolutely nothing. So again, this goes in the same direction. Even though the perception of phases versus non-phases seems normal, the differentiation between different types of phases, these strange sort of scrambled versus unscrambled phases, is clearly different. So since we now found this in several experiments across sort of a large group of people, we think we have something. So that's sort of the kind of our research strategy. We're really looking for differences. We often don't find them, but when we find them, then we're sort of tenacious and say, dog found a bone, and now we're really trying to understand what's going on here. So there's definitely something going on, atypical perceptual processing of phase configurations. And the thing that we're thinking about at the moment is it's all in the eyes. I think there was some mention earlier about it's not all in the eyes. At least the eyes are not the portal to the soul, aren't they? But there's something, I think what we believe is, what we think might be the case here is that in phases, the eye region has a sort of prominent status. Among other things, because the eye region is really important for phase identification processes. And if there's some spatial disruption to the eyes, to the relative location of the eyes relative to the rest of the face, the brain sort of puts up the red flag and says there's something not quite right here. And it could be the case that in people with DP, the eyes don't play this prominent role. And therefore making this disruption, sort of presenting the eyes at an odd place, either by inverting the face or by scrambling the face, doesn't make such a difference. And what we are doing at the moment, what we've actually started, is a sort of new series of experiment that's a bit more subtle than this, where we're actually having other ways of trying to find out whether the eyes are sort of relegated to an also-ran in DP, where they are much more prominent in controls. So is it all in the eyes? That's a study that is currently run by Katie and John and Joanna, and we would be absolutely delighted if we could get some of you to participate in this study. I won't say more about it because we don't want you to see the stimuli. But it's very exciting. So we are all excited about it, but we'll see how long this excitement lasts. Okay, so that's one thing. We believe that there is some sort of something related to the prototypical configuration of the eyes that is sort of slightly different in DPs with respect to perceptual processing. And there's one other thing that's different, and that's to do with face recognition proper. So up to this point, it's all about faces, scrambled faces. Identity doesn't really come into play because they're all unfamiliar faces. But of course, what DP is really characterized with is impaired face recognition, so the recognition of individuals. So we've done several studies where we've wanted to see whether this impaired face recognition is actually due to the fact that there are no memories of a particular face that you could match. So for example, if you see Tony Blair and you say, I don't know who this person is, this can have two reasons. One reason is you have never really established some sort of pictorial representation of Tony Blair in your face memory. There's a sort of big collection in somewhere in your temporal cortex that has sort of all the faces I have ever seen, sort of little picture book. And maybe in DPs, either there's no picture book, or these pictures are so blurred and distorted that you cannot actually match Tony Blair to one of the entries in the picture book, and therefore face recognition doesn't happen. Another possibility is that the picture book is fine. The problem is that from activating this sort of pictorial representation of Tony Blair, there is no further access to further information because there is also the semantic information. Tony Blair is a politician who started the Iraq War and stuff like that. And even though you might be able to say, this person is familiar, if that's where it stops, so then there's no further link towards the sort of semantic entry, then another entry is simply a person with a face like this, the name of this person is Tony Blair and his profession is a politician, so all kinds of entries. If there's something cut between face memory, visual face memory, and all the other semantic entries, then this could be leading to exactly the same sort of behavioral effects. You say, I don't know this person. Maybe there's a vague feeling of familiarity, but normally your task is not to report a vague feeling of familiarity. You have to report, who is this person? And what we found, sort of to cut a long story short, is that we think it's the latter. We found that in many people with developmental prosopagnosia, this mental picture book seems to be pretty intact. So there are sort of stored memories of individual faces, which we can actually see with our EEG technique when we present. So for example, some of you have taken part in this experiment where we presented Tony Blair and 80 familiar faces. And we found that in many DPs, there was actually this picture book, this mental image activation of stored representation was fine, even on trials where they said, I don't know who this person is. And a later component that is related to this sort of conscious recollection of personal identity and all kinds of semantic information, that was absent. And I'm going to show you one experiment at the, now just to illustrate this point. And that's an experiment that some of you have participated in, that Joanna ran. That was the Joe experiment. And we ran this because several of you told us that under certain conditions you find it difficult to recognize yourself, your own face in the mirror, or so that sort of inspired us. So that was actually, in a way, what are called user-led research. So there was is this really true? Is when you're confronted with your own face, is there any evidence that the brain actually recognizes your own face? So because there's anecdotal evidence is sometimes that doesn't happen. So we constructed this Joe experiment where the official task was to find this character here. So that was Joe. We showed them to you, Joe to you in sort of 3 different orientations, so a bit of learning. This is Joe. Respond whenever you see Joe. And during the experiment, on a few trials you actually did see Joe, and then there was the, okay, you had to respond. Then there were loads of unfamiliar faces, and then what we also did is we smuggled in your own face. So it was not such a sort of clever cover story, because when you came in, Joanna took you and said, I would like to take your photograph. And I wonder whether at that point you might already have thought, well, I might see this photograph again, which is exactly what happened. So it didn't come as a surprise, really. And actually, this is Joanna here, but I mean, we did take your photograph. So we just wanted to see whether unexpectedly seeing your own face under conditions where the task actually, there was completely task irrelevant because your task was to find Joe, not your own face. Would you find this activation of face memory both for your own face but also for Joe, because obviously Joe was the task relevant face. And this is our control group. I'll just sort of guide you through this. These are all kinds of visual ERP components, which we don't really need to go to in any detail. So this is sort of time. This is sort of 700 milliseconds after the stimulus has been presented. And the important lines are the red line, that's your own face. The green line, that's Joe. And the black line is an unfamiliar face. And we can tell, and these components we know have to do with visual face memory. So about a quarter of a second, actually a little bit earlier, 200 milliseconds after the face is presented, in the control group, the brain registered, this is my face. It actually registered the presence of my own face about 50 milliseconds earlier than the presence of Joe. Joe was task relevant, so you were looking for Joe. But when unexpectedly your own face came, visual face memory is activated even earlier. That's how important the entry of your own face in visual face memory is. And then after sort of about half a second, we had this other component, which we call our conscious recognition component. So this is visual face memory has registered a match between a picture, in this either your own face or Joe, and then about 200 milliseconds later, it has sort of been transported to some sort of semantic store and says, this is Joe, or this is me. And now, of course, this is the control group. And now we wanted to know whether our DP group had exactly the same pattern. Now, if the anecdotal reports were true that you cannot recognize yourself in the mirror, then maybe this sort of early visual memory component would be completely gone. Nothing registers when you see your own face. But that's not what we found. This is the DP group, and it's quite amazing. The visual face memory was exactly the same. So again, you can see Joe, starting at about 220 milliseconds. This is your own face. Red is your own face. So after 200 milliseconds, your own face is being registered. About about 100 milliseconds later, Joe is registered. So this is almost a carbon copy of what we see in the sort of non-impaired control group. So in spite of the fact that maybe subjectively you feel you find it difficult to recognize yourself in the mirror across all DPs tested, there was absolutely no difference with respect to the sort of visual face memory. So there is a mental image of your own face, and that is being activated when you're suddenly confronted with your own face. No problem, visual face memory is fine. And of course also Joe. So you did store a visual image of Joe, who was the target face, and when Joe came up, something in your visual face memory was activated. Now, as I said at the beginning, we are really interested in differences. So what we then found was that this later component that is related to conscious recognition was much delayed and almost completely absent. Depends exactly on which electrodes you look, but there was a strong attenuation and delay. So this is sort of the illustration that even though the memory, the visual face memory, is being activated by the presence of your own face, say, it somehow doesn't get through properly. It doesn't tell the sort of higher quarters, sort of the command central executive system of the brain, this is my own face. And that can very often then lead to the subjective experience that maybe I don't know who that is. Is that really me? And talking about the cables again, and John mentioned this as well. So we have some problem in face perception that we've identified maybe to do with the faces. It is amazing that stored visual face memories seem to be largely intact in DP. and we have the conscious recognition, and maybe there is something going on here. So we have two areas where we feel that it's promising to look if we wanted to look at differences. One is the sort of perceptual area, and one is this link between the visual face memory and the conscious recognition. And these are the two parts, two areas that we are going to investigate in future experiments. Okay, that's actually what perception of face configurations is different, and links between visual face memory and conscious face recognition. Now, I should say this is all across a larger group of DPs. And one thing that's clear is that there's lots of variation. There's also lots of variation in the normal population. So we have a sort of almost gradual overlap in some of these components. So we sometimes have people who have no face recognition difficulties who still show a rather atypical pattern of these brain responses. And we have some people with DP who sometimes show a typical pattern. So what we're looking at here is not a sort of one-to-one correlation in the sense that whenever you report with prosopagnosia or whenever your Cambridge face memory score is sort of below here, then we know exactly what your brain looks like. We are more like sort of talking here from a probabilistic or statistical perspective, that across a large group of people, we find that they cluster in one way or the other, which doesn't mean that it doesn't mean that each of you, I would be able to say, this is what we're expecting in terms of visual face memory. So we're talking here about sort of groups. And that's also the difference to the medical model, when if you have a kidney stone, then you have a kidney stone, and there's no two ways about it, and there's no statistics needed, you just have to take them out. In this case, it's really more sort of gradual and smeared. But I think there is progress. I mean, that's how I started, is did we actually learn anything over the last 3 or 4 years? I think we did. We now get a better feeling about where we are more likely to find systematic differences. And these two places that I've highlighted here, configuration, perception of face configurations, and this link between visual face memory and conscious face recognition, these are the two things that show up after a while. We didn't expect it to be exactly in this place, but this is where we're sort of being guided towards as the two areas where we do find most of the differences. And so there is progress, and hopefully next year I can tell you even more about where we are going from here. And of course, you know all of these people, John and Joanna and Angie and Brad and Sue and Katie and Frederica and Anna all contributed in their own ways. And of course, again, I said that at the beginning, I have to say it at the end, the ESRC has been so nice to us and has hosted us and was also able to give a little bit of funding for this meeting here. Great, so that is my progress update. More next year.